In the battery world, one thing is becoming more and more clear. Lithium iron phosphate batteries will dethrone lithium ion as the battery chemistry of choice for the short-term future. Why is this happening? Stick around and find out. Lithium-ion batteries have become extremely common and power almost all of our small electronic devices with permanent batteries inside. The term lithium-ion is a general term that includes many battery chemistries, including lithium iron phosphate. But for this video, lithium-ion refers to batteries that have a lithium cobalt oxide or lithium manganese oxide cathode. And lithium ferrophosphate, or LFP for short, has a cathode made of lithium iron phosphate. Lithium-ion is an older technology and led the charge as smartphones, tablets, laptops, and other portable electronic devices became common. These types of devices are high drain and as small as possible. Lithium-ion has a high energy density at 150 or more watt-hours per kilogram, which was perfect for the application. For comparison, lead acid, used in many deep cycle or starting batteries, have only 30 to 40 watt-hours per kilogram, and alkaline batteries, which are common in AA and AAA batteries, start at about 85 or more watt-hours per kilogram. And finally, LFP batteries have 90 or more watt-hours per kilogram. So why would LFP take over for lithium-ion in the future if it has a lower energy density? There are two main reasons and a few minor reasons. The first main reason is safety. We all probably remember the Samsung Galaxy Note 7 phone that was released in 2016 and immediately recalled after phones started catching on fire. This unfortunate situation highlighted a huge weakness of lithium-ion batteries, which is their tendency to enter an unstoppable exothermic chain reaction if they get too hot. Starting at around 60 degrees Celsius on up to 100 degrees, the battery can release all its energy at once and start a fire. This can also happen if the battery is punctured or damaged. So as manufacturers tried to push the battery design further and further to get every last watt-hour of capacity, keep them as small as possible, and make them recharge faster, they reached the limits of physics and put people's safety in danger. LFP batteries do not have this weakness. LFP has excellent thermal and chemical stability and does not combust when short-circuited or damaged. The second main reason is environmental. Lithium-ion batteries are hazardous materials which can cause problems when exposed to human skin or eyes, or severe issues if swallowed. They require special recycling or disposal procedures and can be dangerous if they end up in landfills. To make things worse, cobalt mining for the cathode materials has significant humanitarian and environmental issues as well. And the supply of the element nickel cannot keep up with the rapidly rising need for batteries, resulting in higher and higher costs. Same with cobalt. LFP batteries, on the other hand, are non-toxic and made from more common materials without these concerns. The other minor reasons LFP is going to take over for lithium-ion is it has a longer cycle life, longer shelf life when not in use, costs less, and stays cooler when discharging or charging. All of these advantages make it better suited for most applications, especially the booming prospects of electrical grid storage. Now, you don't have to just take my word for it. In the last year or so, there have been numerous news articles on this subject, and recently Elon Musk, founder of Tesla, has gone on record saying that nickel is our biggest concern for scaling lithium-ion cell production. That's why we are shifting standard range cars to an iron cathode. Plenty of iron and lithium. As the emerging markets of mass-produced electric vehicles and stationary energy storage to support solar and wind energy grow, there's little doubt that the popularity of lithium iron phosphate will grow with it. There are still advancements to be made with LFP chemistry, and many of these new markets don't require quite as high energy density. But what about other battery chemistries? It seems like we hear about a new wonder chemistry or battery discovery every week that promises to be the next big thing. The reality is that most of these discoveries are in their infancy and are still being tested and built in science labs at universities. It's one thing to make a small prototype in a lab in a controlled environment with a huge budget. But being able to mass produce these chemistries and certify that they're safe and viable takes decades. But there is another variation of lithium battery chemistry that is being touted as the immediate answer, and that is lithium nickel manganese cobalt oxide, or NMC for short. NMC is a newer technology than LFP and does have advantages. However, as the name suggests, it still requires nickel and cobalt to produce, is more expensive than LFP, and studies are showing that it doesn't last nearly as long. So the jury is still out on NMC, and many technological advancements will surely follow to bridge the gap. But for now and for the next 10 years or so, it looks like LFP will be the king. Thanks for watching this video. If you're excited about the future of LFP, consider subscribing to my channel and checking out some of my other content.